Good day, students. Last time we have discussed about the concepts behind the Hamiltonian formalism. Today, I will give you two examples and I will teach you how to obtain the Hamiltonian formalism and its corresponding equations of motion. And later on, you can see that you can still use the Lagrangian formalism to get the Hamiltonian formalism. Okay, so start ata. So our first example is about an oscillating cart of mass m uh, that is oscillating on the end of the spring along the horizontal frictionless surface. So the question is to find the Hamiltonian formalism and its equations of motion. First, we try to understand the mechanics behind the system. As you can see in this diagram here, the cart is moving on a frictionless surface along the x-axis. So take note that there is no movement along the y-axis. Thus, we can conclude that velocity along the y-axis is 0, or y dot is equivalent to 0. Note that this system has only 1 degree of freedom since the cart is translating only along the x-axis. The equation of the kinetic energy is just the translational kinetic energy along the x-axis, that is just 1/2 mx dot squared. So another way or another energy to consider in this system is the elastic potential energy due to the spring, no, given by U is equal to 1/2 kx squared. So after getting the kinetic and potential energies, we can now formulate the Lagrangian formalism. So using the equation L is equal to T minus U, where T stands for the kinetic energy and U for the potential energy. So the Lagrangian formula is now equivalent to 1/2 mx dot squared minus 1/2 kx squared after plugging those equations. Okay. In order to get the Hamiltonian formalism, first we need to obtain the generalized momentum in the form of px is equivalent to partial derivative of the Lagrangian L with respect to x dot. Okay, so simplifying this equation, as you can see here, we get the px is equivalent to mx dot, and manipulating the equation, we can express x dot in terms of the momentum x. So x dot is equal to px over m. We can use the general form of the Hamiltonian formalism using this formula, where h is equal to the sum of pi times q dot I minus the Lagrangian L. Okay, so where pi is equivalent to px and q dot is equivalent to x dot. So the technique is to retain the generalized momentum px and just substitute the equation for the x dot as we have obtained just earlier, no? Then we can obtain this equation. Okay, simplifying the previous equation, we get this again, we get this equation, and finally we have obtained the final form of the Hamiltonian, that is the sum of the kinetic energy expressed in generalized momentum px or that is just px squared over 2m plus 1 half kx squared. This one here is the equation for the potential energy. Okay. Then our next move is to find its equation of motion. Okay, muna na tagkuha sa Hamiltonian formalism. So, and take note that the Hamiltonian formalism is different from the Lagrangian. If the Lagrangian formalism has n numbers of equations, which is expressed in second order differential form, then Hamiltonian has 2n number of equations, okay, equations of motion, which is expressed in the first order differential form because of these two terms here. That is p dot I and the q dot. Okay. So for p dot I, that is equivalent to p dot x. That is just the negative partial of h with respect to x. We get the minus kx. And x dot, that is just the partial derivative of the h with respect to px. So we get the px over m. And take note that this p dot x here is equivalent to kx, that this equation here implies that this is the restoring force of the oscillating cart due to the massless spring, as you can see here in the diagram. Okay, so nakuha na nato ang duha ka equations of motion from the Hamiltonian formalism. So our next example is about the simple pendulum. Okay, so a bob of mass m is attached to a massless string of length L hanging on the fixed point at the ceiling. So the question is to find the canonical momenta and canonical velocity of the simple pendulum. So if we analyze the problem, the bob was able to swing back and forth due to gravity. Thus, obtaining the equation of the positions x and y is required to get its corresponding velocities. So we can freely use the Pythagorean theorem to get those equations, such as x now has an equation of L sine theta and y is equivalent to L cosine theta. And take note that the height of the bob is also important to determine its gravitational potential energy later. So H is equivalent to L cosine L minus L cosine theta, and the corresponding x dot, okay, gikan siya sa total derivative sa x ng equation. So x dot is equivalent to theta dot times L cosine theta. And kaning y dot bot gikan pud siya sa total derivative din niya sa equation nga y. So that is equivalent to negative theta dot times L sine theta. So plugging this x dot and y dot to the equation for the kinetic energy, we obtain T is equivalent to 1/2 ml squared theta dot squared. Okay, so nakuha na nato ang kinetic energy. So our next move is to find the potential energy of the system. So that is just U is equivalent to mgl times the quantity 1 minus cosine theta. So iguro na to gi-substitute or gi-plug in ang value sa value or equation sa height. Okay, and we can obtain the Lagrangian formalism by plugging the equations of the kinetic energy and U. So this is now our Lagrangian formalism. Okay, and as we have done in the previous example, we can express or find the uh, generalized momenta p theta, no? So that is just the partial derivative of Lagrangian L with respect to theta dot. So we obtain p theta just equivalent to ml squared times theta dot. So manipulating this equation, we can express theta dot in terms of p theta. Okay, that is over ml squared. So again, using the general form of the Hamiltonian formula, which is the summation of pi times q dot I minus L, such that pi is equivalent to p theta and q dot is equivalent to q dot. No, theta dot. Okay. So we have h is equivalent to, okay, sa atong gibuhat sa ato ang previous example, we need to retain the generalized momentum p theta and just plug in the equation for the theta dot. So nakuha na to ang equation sa theta dot as previous na to nga slide. I-plug in lang na to ang equation sa diniya. So we obtain this equation, and simplifying further the Hamiltonian equation kani siya, we finally get the Hamiltonian formalism, that is just the equivalent of p theta squared over 2ml squared plus mgl times the quantity 1 minus cosine theta. So dili pa gid ta dinhi tama, no, kay pangitawan pa nato ang equations of motion or the canonical momenta and the canonical velocity sa Hamiltonian formalism. So again, we can use these two equations here to find the equations of motion. Okay, so p theta dot is equivalent to the negative of the Hamiltonian with respect to theta, and we obtain an equation of negative ml squared sine theta. Respectively, we get the value or the equation for the theta dot, that is just the partial derivative of the Hamiltonian with respect to p theta. So we obtain p theta over ml squared. So and that's it. Hope you understand these two basic examples. To further, so for further understanding on the Hamiltonian formalism, you can solve this problem as your assignment and pass it during our lecture time. Okay, so assignment is, as you can see here, you can use the potential energy here, that is just equivalent to minus k cosine theta over r squared, no? So you need to find the kinetic energy using the spherical coordinates and determine its equation of motion from the Hamiltonian formalism. And that's it. Thank you and God bless.